In this lesson, we'll determine the power series solution to Airy's equation, which is y double prime minus xy equals 0 near the point x sub 0 equals 0. Comparing the form of Airy's equation to the form shown here on the right, notice p of x is equal to 1, and since p of x sub 0 or p of 0 equals 1, not 0, x sub 0 equals 0 is an ordinary point. Recall if p of 0 was equal to 0, we would have a singular point. But because we have an ordinary point, we try y equals a sum from k equals 0 to infinity of a sub k times x to the power of k. And now we need to work on determining y double prime. On the right, I've shown y prime, where y prime is equal to the sum from k equals 1 to infinity of k times a sub k times x to the power of k minus 1. Notice we simply applied the power rule differentiation, but also notice how the lower limit of the sum is now k equals 1. This is because the first term in y is a constant and the derivative is 0. Similarly, to find y double prime, we apply the power rule and the lower limit of the sum becomes k equals 2 because the first term in y prime is also a constant and the derivative is 0. So we have y double prime is equal to the sum from k equals 2 to infinity of k times k minus 1 times a sub k times x to the power of k minus 2. And now we perform substitution with y double prime and y into the differential equation. Recall the differential equation is 0 equals y double prime minus xy. So we have the power series for y double prime minus x times the power series for y. Next we multiply x into the sum for the power series of y, which gives us the sum from k equals 0 to infinity of a sub k times x to the power of k plus 1. And now we reindex the power series for y double prime, so the lower limit of the sum is k equals 0. To do this, we replace k with k plus 2, which I've shown here on the left in blue. Replacing k with k plus 2 gives us a sum from k equals 0 to infinity of k plus 2 times k plus 1 times a sub k plus 2 times x to the power of k. Now from here though, if we find the first term when k equals 0, we have 2 times 1 times a sub 2 times x to the 0, which gives us the constant 2 times a sub 1. So now we write this power series as 2a sub 2 plus the sum from k equals 1 to infinity of k plus 2 times k plus 1 times a sub k plus 2 times x to the power of k. And now because this sum starts at k equals 1, we need to reindex the power series for y shown above, so the lower limit is k equals 1, not k equals 0. We do this by letting k equal k minus 1. Performing this substitution, we now have the sum from k equals 1 to infinity of a sub k minus 1 times x to the power of k. From here, because both sums start at k equals 1, we can combine the two sums. We can also factor out the common factor of x to the power of k. So in the next line, we have 2a sub 2 plus the sum from k equals 1 to infinity of k plus 2 times k plus 1 times a sub k plus 2 minus a sub k minus 1 all times x to the power of k. Now again, remember the differential equation is equal to 0, and therefore 2a sub 2 plus the power series must also equal 0. To begin, that means 2a sub 2 must equal 0. Recall a sub 2 is a constant, and therefore a sub 2 is equal to 0. Similarly, all the coefficients of the power series must also be 0. This gives us the equation k plus 2 times k plus 1 times a sub k plus 2 minus a sub k minus 1 equals 0. Solving this equation for a sub k plus 2, shown on the right, we have a sub k plus 2 equals a sub k minus 1 divided by the product of k plus 2 and k plus 1. Analyzing this recurrence relation, because we have a sub k plus 2 on the left, and on the right we have a sub k minus 1, we jump in steps of 3. And since a sub 2 is equal to 0, we have a sub 5 equals 0, a sub 8 equals 0, a sub 11 equals 0, and so on. Notice we're adding 3 to the subscript each time, and the value is 0. This should make sense because if we were trying to find a sub 5, notice k is equal to 3, and therefore the numerator is a sub 3 minus 1, or a sub 2, which we know is 0, indicating a sub 5 is 0. We get a similar result for a sub 8, a sub 11, and so on, which means in general a sub 3n plus 2 is equal to 0. The formula 3n plus 2 gives us the subscript 2, 5, 8, 11, and so on. In addition, the constants a sub 0 and a sub 1 are arbitrary. So if we go to find a sub 3, notice k is equal to 1. This indicates a sub 3 is equal to a sub 0 divided by the product of 3 and 2. To find a sub 4, notice k is equal to 2. A sub 4 is equal to a sub 1 divided by the product of 4 and 3. And we know a sub 5 is 0, so we'll go to a sub 6. We'll also write a sub 6 and the remaining terms in terms of a sub 0 or a sub 1. So to find a sub 6, notice k is 4, which gives us a sub 3 divided by the product of 6 and 5, but a sub 3 is equal to a sub 0 divided by the product of 3 and 2. Performing the substitution, we have a sub 6 equals a sub 0 divided by the product of 6, 5, 3, and 2. We'll go ahead and find one more term. For a sub 7, notice k is 5, giving us a sub 7 equals a sub 4 divided by the product of 7 and 6, but a sub 4 is equal to a sub 1 divided by the product of 4 and 3, and therefore we can write a sub 7 as a sub 7 equals a sub 1 divided by the product of 7, 6, 4, and 3. And now we need to analyze these terms to recognize a pattern. Notice when the subscript is a multiple of 3, meaning a sub 3 and a sub 6, the numerators are a sub 0, and then if we analyze the factors in the denominators and reverse the factors, for a sub k, where k is a multiple of 3, we have k equals 3n, and we notice that a sub 3n is equal to, again, a sub 0 divided by the pattern for the factors in the denominators are 2 times 3 times 5 times 6, all the way out to times 3n minus 1 times 3n. So notice for a sub 3, n is equal to 1, and the factors in the denominator would be given by 3n minus 1 and 3n, which are 2 times 3 or 3 times 2. And for a sub 6, n is 2. The largest two factors in the denominator would be 3 times 2 minus 1 or 5, and then 3 times 2, which is 6, and we still have factors of 2 and 3. So this formula may be a little challenging to come up with, but it does work when the subscript is a multiple of 3. Similarly, for a sub k, where k is equal to 3n plus 1, meaning a sub 4 and a sub 7, we have a sub 3n plus 1 is equal to a sub 1 divided by the factors given by the pattern 3 times 4 times 6 times 7, all the way out to times 3n plus 1. For a sub 4, notice n is 1, and the factors in the denominator are given by 3n and 3n plus 1. For a sub 7, when n is 2, the two largest factors in the denominator are given by 3 times 2 and 3 times 2 plus 1, which are 6 and 7. But we also have factors of 3 and 4. And now we'll take the formulas for the coefficients given by a sub 3n and a sub 3n plus 1 to write out the power series solution. When writing out the terms, though, we will multiply out the denominators. Notice for a sub 3, the denominator will be 6. For a sub 4, the denominator is 12. For a sub 6, the denominator will be 6 times 5 times 3 times 2, which is 180. And the denominator for a sub 7 will be 7 times 6 times 4 times 3, which is 504. So we have y equals, first using the formula for the coefficients of a sub 3n. When n is 0, we have a sub 0, plus again, when n is 1, we have a sub 0 divided by 6 times x cubed. When n is 2, we have a sub 0 divided by 180 times x to the 6th, and then plus dot, 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 using our formula. And then plus, using the formula for a sub 3n plus 1, we have a sub 1x plus a sub 1 divided by 12x to the 4th, plus a sub 1 divided by 504x to the 7th, plus dot, dot, dot. From here, we can factor out a sub 0 from the first set of parentheses and factor out a sub 1 from the second set of parentheses, and then define y sub 1 of x and y sub 2 of x, where the constants a sub 0 and a sub 1 are arbitrary. Now that we've defined y1 of x and y2 of x, we can write the general solution to the equation as y of x equals a sub 0 times y1 of x plus a sub 1 times y sub 2 of x. And if we plug in x equals 0 into the power series for y1 and y2, we can see that y1 of 0 is equal to 1 because all the other terms have factors of x, and y2 of 0 is equal to 0 because all the terms contain a factor of x. Similarly, y1 prime of 0 would be 0 because all the terms in the derivative would contain a factor of x, and y2 prime of 0 would be equal to 1 because the derivative of x is 1, all their terms have a factor of x. Therefore, we have y equals a sub 0 y1 plus a sub 1 y2 is a solution that satisfies the initial conditions y of 0 equals a sub 0 and y prime of 0 equals a sub 1. And the two solutions, y1 and y2, are graphed here on the left. Again, these are two solutions to Airy's equation. And finally, before we go, the functions y1 and y2 cannot be written in terms of the elementary functions that we know of. Looking at the graph below for the plot of y1 and y2, these functions have many interesting properties. For example, they are oscillating for negative x values, like the solutions to y double prime plus y equals 0, and for positive x, they grow without bound, like the solution to y double prime minus y equals 0. I hope you found this helpful.